Hello everyone. Welcome to ComSci Connection recursive merge sort example. This is going to be the demonstration on computer. It's not going to be an explanation of how this works in detail. If you really want to see that kind of stuff, we will have a merge sort tutorial video up at some point, but as of right now there's a Blackboard walkthrough of the process, and that's really where I explain basically the general concepts of merge sort. It's still not a complete explanation of exactly how to do it or how to write merge sort on your own, but it's enough to get you understanding how it works and how to repeat that code or duplicate that code on your own. This is my own version of merge sort. What I'm going to do here is explain to you basically how this is going to work, and I'm going to show you how it looks in terms of the recursive function of this algorithm. So one thing I'm going to mention to start out with is that we're going to make a size 11 array. We're going to initialize that with random values. For this purposes of this, I'll just make them up to 100 max value. So we are going to print the elements to the screen. As you can see, I've already ran this once just up to that point, so you can see what that's going to look like. And then it's going to call merge sort. It's going to call merge sort on the entire array here, but it's providing these bounds 0 and r length -1, which is basically the left and right bounds of the subarray, which in this case is the entire array, that need to be sorted. So 0 is going to be passed in as the variable left, and the length -1 will be passed in as the variable right. So that's the true left and true right bounds of the entire array. So it's basically saying, hey, sort my entire array. This is basically the main thread at which finally, once it returns to this point, our array is going to be completely sorted. And then it'll print out the elements again for us to see that. In merge sort, it's actually going to do the splitting that defines merge sort. It's going to split the array into a left side and a right side, and then call recursively the merge sort method again on those halves until it eventually ends up sorted. The magic will happen. And one thing I'm going to quickly explain, but I'm not going to show the process take place because it's not recursive, is this merge method that will basically actually merge the two halves back together. And I'm just going to tell you that merge is actually where the sorting takes place. If you are a little confused on that, or if you don't really understand that process, refer back to the other video, which is the Blackboard walkthrough, where I explain how it does it and explain a little bit about what the advantage is of using merge sort versus something like bubble sort, because you know that the left side and the right side are both already sorted by the time that happens, and that's really the magic of merge sort. So you know that the first element in the left subarray is going to be the smallest every single time, and then increasing, and the first element in the second subarray is going to be the smallest in that subarray every single time, and then increasing after that. So you only have to check the first element of each subarray, determine which one's smaller, copy that one into your original array, then increase the counter on that subarray by 1 until you run out of elements in that subarray, and then you just copy the other subarray and then that will give you a sorted array in the end. So that's kind of what merge does, but the magic of that is, I'm just telling you that that's where the sorting takes place, is that line right there. But the magic is that even though my method here will call merge sort recursively on the left side, then call merge sort recursively on the right side, by the time it reaches this line of code, this merge, which says to do the sorting, you have to understand that the left side and the right side are already sorted by that point. And why is that? Well, it's because in the recursive calls, which become higher priority on the stack and must complete and fully execute before they can return to the point at which they were originally called, here and here, by the time those lines have returned back to that point, merge has been called on those higher level recursive calls. So the first execution of merge sort here, which will be given the entire bounds 0 and size -1, will actually not execute this until after merge has been executed on every other level of the recursive calls. And if that's a little bit confusing, then I recommend that you go back and refer to the Blackboard video, but this will kind of illustrate that process here. So let's just go ahead and get right into it. Run debug, and we will see this process take place. So let me make this console a little smaller. and this a little bit smaller. Alright, so we're going to go ahead and call merge sort on the entire array. Let's step into that. Now our base case here says, can we split this any farther, or can we not split this any farther, I should say, because it's saying if the left bound is greater than or equal to the right bound, then the greater than is just kind of there as a safety measure. But if, in other words, if there is more than one element in our current range, so if left is 1 and right was 1, then there's only one index there. So you can't split that into half of an index or anything like that. So that is saying if I cannot split this any farther, then I go ahead and return, which means that no matter what number of elements I pass into this function, at some point it's always going to come down to a point in a recursive call where there's only one element, and that's the point at which the dominoes of the recursive calls are going to start to fall back and do the merging, and you'll see that here. But obviously right now left is 0, right is 10, so the base case is not true. So we're going to define a midpoint of the array, which will basically determine where we're going to split it at. Right minus left divided by 2 plus left is going to give us the midpoint, which at this point is going to be 5. So that's exactly half of 11 in integer division. So we're going to go ahead and call merge sort on the left side, which we've just defined. If we know the mid, then we know the left. The left would be original left, which will become the new left on the new recursive call, and mid, which will become the new right on the next recursive call. So we're going to go ahead and step into that. Now, one thing I'm going to point out here is that, look, the other recursive, or the original call to merge sort is still there on the stack, just like this one on main, it's still there. It's at this line right here, and it's waiting. It can't do anything else until the original call to merge sort has finished and returned its information back to this point. Same thing with this merge sort. It just called merge sort again. This is the recursion. It called itself the same function again, but it exists in another dimension, if it helps to think of it that way. This merge sort still exists. It still has left 0, right 10, and mid 5, but it is a whole nother animal at the same time. This new merge sort has been created with bounds left 0, right 5, and it doesn't care or need to know anything about the previous call, nor does the previous call need to know really anything about this call. It just needs to do what it needs to do, and by the time it gets back to, well, by the time this method completes, this one's ready to move on to the right side. And that's the importance. That's the magic of the recursion in this algorithm. So I'll go ahead and step through. Obviously we know left is 0 and right is 5. They aren't the same, so we can still split this farther. So let's define a new midpoint, which will be 2. Now we're going to go ahead and step into merge sort again. So 0 is going to be passed in as left, and 2 is going to be passed in as the right. So now we've created another element on the stack. We've got another call to merge sort, which is now higher priority, and this previous one here, they have to wait until this one can finish. So we know that left is 0, right is 2. That's not going to be the base case. We're going to define a new midpoint, which is going to be 1, and then we're going to recursively call merge sort with the bounds 0, 1. Step into that. We know that 0 and 1 is a size 2 array, so it's not the base case. We're going to define a new midpoint, which is going to be 0. So now we're going to end up calling merge sort with the bounds 0 and 0, which of course we know is a size 1 array. So it's going to say, well, left is equal to right, so I'm going to go ahead and return. Bam! Left side is done. We are complete with the left side on this stack. This one is still waiting for its left side here, where the bounds were 0 and 2. This one's still waiting for its left side, where the bounds were 0 and 5, because we haven't completed the higher level recursive methods. They haven't finished and returned. So now we're on the right side of this one, where the bounds are 0 and 1, and the midpoint is 0. We'll go ahead and recursively call into that, which is going to be mid, which is 0, plus 1 is 1, and right was 1. So again, we know that left and right are both 1, which means that we have a size 1 array, meaning that we are going to go ahead and return. So now, on this level of the stack, where we have 0 as the left bound and right as the and 1 as the right bound, we have a size 2 array, and we've just split the size 2 array into 2 size 1 subarrays, and they have the values 51 and 85. Well, we know that 51 is actually smaller than 85, so no actual change is going to be made to the original array. But as I said, I'm not going to step into merge anyway because it's not going to demonstrate recursion at all. It just does what it does, and you can trust me on that. So skip over that, but that means that this level of the stack is complete. We've got left is 0 and right is 1, and we divided them into 2 subarrays. We sorted them back together, which meant we did no change in this case, and then we're going to go ahead and return. Remember that even though there was a left side of this one and a right side of this one, of this level of the stack, that still is only considered the left side of the stack element that was higher up on the list, or lower, I should say. That's still waiting for left here. So 0 to 2 was 0 to 1, excuse me, was passed in as bounds for this call to get the left side for bounds 0 to 2. If that didn't make sense, rewind like 30 seconds and listen to what I just said again. 0 to 2, its left side was 0 to 1, but 0 to 1 had to divide a left side of 0, 0 and a right side of 1, 1. Okay, so now we've finished sorting that side, so we're going to go ahead and step over, and this is going to fall off the stack. It's going to disappear. Now we're on to the right side of 0 to 2, which is going to pass in mid plus 1, which is 2, and right, which is 2. So that is a size 1 array. So we're going to go ahead and step into that. We're going to see left and right are both 2, and then that means we're going to immediately return. So now what do we have on this level of the stack? We have left 0, right is 2, mid is 1. So we know we had a size 2 array, that's the left side of this level of the stack, and we have a size 1 array, that's the right side of this stack, and now we're going to merge those two back together. So we know that this is basically our left side here, 5185, and this is our right side, just this one element, 21. What will happen is that 21 will be evaluated against 51, 21 will be proven to be smaller, it'll be placed here. Then, since there's no more elements in the right side of the right subarray, it's going to immediately copy the elements in order from the left subarray into the actual array. So we're going to end up with 21, 51, 85. And I'm going to go ahead and step over this merge call, and you're going to see exactly that, 21, 51, 85. So this is just 0 up to 2. But since this has now completed, these two halves have now completed, this is considered the left half of the call to merge sort that is one lower on the stack than this recursive call. So we're going to go ahead and step over. This is going to fall off the stack, saying it's completed merging these two halves back together, and now it's considered one half again, the left half. The left, we're back onto the level of the stack where left was 0, right was 5, and mid was 2, and we have this basically defined as the left half. So now the right half is going to be 3 up to 5. So we're going to go ahead and step into that. Left bound 3, right bound 5, we can still divide that. We're going to define a new mid, which is 4. We're going to go ahead and recursively step in where left side is 3, right side is 4. We can still divide that, so we're going to define a new midpoint as 3. We're going to step into that. Left is 3, right is 3, that's one element, so that would be this one, number 8. So we're going to go ahead and return. Now we've got to define the right side of this level, and that's going to define left is 4, right is 4, which is this element here, 19, so we're going to return. Now we've got two elements to compare, the left side and the right side, or the left subarray and the right subarray, and these are going to obviously not switch, so we're just going to step over merge and nothing changed because left is less than, because 8 is less than 19. So now we're going to step back because these two elements have been merged and they're considered the left side of the call where left was 3 and right was 5. Mid's 4, so we'll step into this. Right, the left is 5, right is 5, so we're going to return that being one element. So it's the same thing that just happened on the previous set where we had 3 numbers. We now have 3 numbers. This is the right side, it has size 2. This is the left side that has size 2, excuse me, and this is the right side that has size 1. Now you'll actually notice, as I just noticed now, that we have two 51s, but they're considered the same element, so they're not going to change when they're compared against each other. They'll just be left alone if they turn out to be next to each other. That's totally normal. But either way, in this case, actually no change is going to be made when we compare this subarray with this subarray, because 8 is less than 51, 19 is less than 51. We'll run out of elements in the left subarray, so we'll copy in the remaining elements of the right subarray, and it's going to basically give us the same result. So I'll step over merge, and then we're going to fall back. Now we're back to the call where left was 0 and right was 5, and our midpoint was 2. We've completed the left side, we've completed the right side, so now we're going to merge the two sides together. So here's the left side, size 3, and here's the right side of size 3. We know that because the previous merge calls, or merge sort calls, had a merge call in them, we know that each one of these subarrays is sorted in respect to itself. So we know that this is the smallest element in this subarray, then larger, and the same thing can hold true for the right side. We know that 8 is smaller than 19, and we know that 19 is smaller than 51. So we're going to go through and compare these against each other, and we're going to end up with this result. 8, 19, 21, 51, 51, 85. And as you can agree, these are sorted order. So we'll go ahead and fall back. Now we're back to our original merge sort call. The left side of this merge sort call is done. It's sorted and it's complete. And this is the magic I was talking about earlier. We know that the merge hasn't actually ran yet on this original call to merge sort, but somehow magically our left side is already sorted because we called merge sort on the left side. Now we're going to call merge sort on the right side. I'm going to step through this a lot faster this time. So we got bounds of left 6, right is 10. We know that that's not the case. We can still split this farther down. So we're going to define a new mid. We're going to call recursively on the left side. Left side of that is going to be 6 up to 8, so we can still split that. We're going to split it some more. We're going to go ahead and recursively call in. The left side is 6 to 7. We can still split that, so we're going to split it. Let's go up to the left side. Left is 6, right is 6, that's only one element. We're going to go ahead and return. Let's recursively call into the right side. Left is 7, right is 7, that's only one element, so let's return. Let's compare the 6th element against the 7th, so 0, 1, 2, 3, 4, 5, 6 against the 7th. We know that 11 is smaller than 45, so they'll switch. And then we're going to fall back. Now we're going to do the right side of this level of the stack, which is going to be 8 up to 8, that's only one element. Let's return. We are going to compare, we're going to merge now 11 and 45 against 34. We know that it'll be 11, 34, 45. Let's skip over it. That's exactly what we've got. Then let's fall back one more level. Now we're back to doing the right side of this bound, 6 up to 10. We're going to step into that. The right side is going to be 9 to 10, which is a size 2 array. We can still split it. Let's define a new mid. Step into the left side. Left is 9, right is 9. That's only one element. Let's return. That would be this element here, 91. Then we have the right side of this subarray is going to be left is 10, right is 10, that's only one element. Let's return. It's going to be 29. Now we're going to be merging the subarray of one element size 91 with the subarray of one element size 29. We're going to obviously switch those, so let's do that. Then let's fall back. Now we've got a left side of these three elements, 11, 34, 45, and a right side of these two elements, 21, 29, 91. What's going to happen is it's going to compare 11 against 29, 11 is smaller. Then it'll compare 34 against 29, 29 is smaller. Then it'll compare 34 against 91, 34 is smaller. Then it'll compare 45 against 91, 45 is smaller. We're out of elements in the left side of the array, so it'll copy the remaining elements of the right side of the array, 91, and we'll be completely sorted on that half. So now I'm going to fall back one more, and we're back again to our original call to merge sort, where left was 0, right was 10, so the entire array, and magically we haven't called merge yet, but we know that our left side is completely sorted and our right side is completely sorted, so now we can go through and compare elements one at a time. And just for stuff and nonsense, I'll go ahead and step into this and you can see the process work. So it's going to go through, it's going to make a helper array, it's going to check the elements against each other. This says while there's still elements left in the left side of the array, and there's still elements to compare left in the right side of the array, we're going to compare those elements. Whichever one is smaller is going to be copied into our helper array, and then we're going to increment the counter for the helper array and the counter for the left side of the array and the right. And then if the other case is true, we'll copy the right side of the array in and then increase that counter. So we'll watch this happen as the elements from this current array are going to be passed into the helper. 8, 11, 19, 21, 29, 34, 45. Somewhere here soon we're going to run out of elements in one of the arrays. Maybe not. Yep. Okay, so now we ran out. There's one element left to copy, and it's in the right side, so it's going to do that. Copies that in. There's no more elements left in that side. We've got our completed array. Copies. It's going to copy this array back into the original. Da 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 da, and done. Now we're done with the original call to merge sort, and we're going to go back to the original main method. It's going to print the elements out to the screen. Those are sorted. We can all agree. And now we're done. That's it. That's merge sort. That's merge sort recursively. And I hope this video helped out. If you have any questions, let us know. Otherwise, good luck. Feel free to watch the Blackboard video, and let us know what you guys think.